module will continue our discussion of best management practices. The information provided in this training can be found in Appendix 1 of the Certified Stormwater Operator and Soil Erosion Control Inspector Training Manual. The lower right corner of each slide will reference where the information on the slide can be found in the appendix. During this section, we will look at the proper installation of some of the common soil erosion and sedimentation control measures used on construction sites. We will start by taking a look at the use of rolled erosion control products on construction sites. Products such as mulch blankets and turf reinforcement mats protect soils and live seed from erosion and provide an environment to promote germination and growth of vegetation. There are two basic types. Temporary rolled erosion control products are designed to reduce erosion for a limited time frame and biodegrade as vegetation becomes established. These products are designed to last anywhere from 3 months to 3 years, depending on the type of material. Turf reinforcement mats are used in situations where permanent structural support is needed. Once grass is established, turf reinforcement mats can be more effective than rock riprap. Pay attention to which mulch blanket was specified in the SESC plan and make sure that particular type of blanket gets installed. The plan designer has chosen a particular product based on a variety of site considerations, including slope and runoff velocity. Straw blankets are used for many applications, but wood or coconut coir may be needed in areas with greater runoff velocity and on the banks of streams and lakes. Here is an example of a temporary rolled erosion control product. This straw mulch blanket has the benefits of mulch, but can be used on steep slopes and in areas of concentrated flows. There are many types of blankets to choose from. If assistance is needed to select the appropriate blanket for a particular site, design software is available to help in making this determination. In areas of channelized flow, it's important to choose high velocity or double-sided netting types of erosion control blankets. Rolled erosion control products are designed to be rolled in the direction of flow. The blanket needs to be trenched at the top of the slope and then installed in a shingled pattern on the downslope. Blankets need to be overlapped between rolls. An overlap of 6 inches is typical, but make sure to check the manufacturer's recommendations. The number of stakes and the pattern in which they are installed is important. The use of stakes or staples should be written on the plan, along with the pattern. The number of stakes needed may vary between 1 to 3 per square yard, depending on site conditions. The plan designer should be sure to check the manufacturer's recommendations. This diagram shows the correct installation of rolled erosion control product in a channel. The top and end are trenched, and each roll of blanket is overlapped with the next roll. The blankets are heavily stapled in this application in order to keep the blankets in place. In this photo, we can see the results of improper installation. So, what went wrong? It's possible that the mulch blanket was not trenched at the top of the slope, which would have allowed stormwater to make its way under the blanket. Over time, rill and gully erosion may result. Other problems could have been the failure to overlap blankets or the lack of adequate numbers of stakes or staples to hold the mulch blankets in place. Here's an actual installation which looks much better. At the top of the slope, a single width of blanket was installed running along the top of the slope on both sides of the channel. The blankets were trenched to prevent stormwater from flowing underneath the blanket and eroding the soil on the slopes. The installers then rolled a series of blankets down the slope, running perpendicular to the blankets at the top of the slope. Along the bottom of the channel, the blankets were again turned in order to run parallel with the channel. Here we see turf reinforcement mat and temporary check dams. Again, this is a permanent structural support for vegetative growth. Once grass is established, the turf reinforcement mat is comparable to 36-inch riprap in preventing erosion. When installing this product, it's important to make sure it's staked well. The product is designed so that grass will grow in the space in between the woven fabric. Make sure that the area underneath the mat is properly seeded and watered as needed in order to promote healthy vegetation. Here's a diagram of installation of mulch blanket on a slope. Again, we see trenching at the top of the hill and mulch blankets installed so they overlap each other. The diagram includes specifications for staple size and spacing. Remember to always check the manufacturer's recommendations, as there may be some exceptions to common installation practices. For example, the manufacturer of Curlex, a blanket made of wood fiber, states that edges do not need to be overlapped for this particular product. In this photo, you can see that the mulch blankets start at the top of the slope and are rolled down slope. At the bottom of the basin, the mulch blankets are installed parallel to the channelized flow. Clearly, a lot of effort was put into this site. The next BMP we'll discuss is diversions. Diversions are used to route water around the work site, which can reduce erosion during construction and promote work in the dry. On some sites, creating a diversion is used as a technique to prevent concentrated flows from reaching a critical or sensitive area. A diversion could also be used to protect a structure on the property. When a diversion is created, flows are concentrated, which can cause additional problems if not managed properly. It's important to design the diversion with adequate capacity to handle high flows during storm events. When we create a diversion, we need to determine the best location to place the diverted stormwater. Placing the water in a well-vegetated area could be a good option if there is a vegetated area on site and if the water is reasonably clean. This will allow the stormwater to infiltrate into the ground. Small amounts of sediment will be filtered by the vegetation. On some sites, a basin is used to settle out sediment prior to the stormwater being discharged to a surface water body. On sites with steep slopes, a grade stabilization structure may be used to convey stormwater from a higher elevation to a lower elevation. At the outlet to the grade stabilization structure, riprap is commonly used in order to dissipate the energy of the water and to prevent erosion at the outflow area. Because there are many factors to consider, diversions should be designed by an engineer. Design capacity is based on risk. For minor buildings and roads, the diversion is typically designed for a 25-year, 24-hour storm event. For major buildings such as homes and schools and high-capacity roads, the basin is typically designed for a 100-year, 24-hour storm event. Velocity of the runoff should be in the non-erosive range. A calculation must be done with the determination based on the specific soil type and vegetation. Increased velocity can be accommodated with the addition of rolled erosion control products in addition to vegetation. Diversions must be inspected at least weekly and after each storm event. Any areas of erosion need to be repaired right away. Most diversions are temporary and need to be removed at the time of project completion. The area where the diversion was located would then need to be final stabilized. The next BMP we'll discuss is sediment basins. Sediment basins are used for collection and storage of sediment-laden runoff. Stormwater runoff is allowed to sit in the basin, which allows larger particles of sediment to settle out and fall to the bottom of the pond. If designed correctly, the stormwater discharged from the basin should be clear. Sediment basins can be effective for removing particles of sand and larger particles of silt. But what about smaller particles, including silts and fine clays? These small particles of sediment do not readily settle out in a sediment basin unless they have some extra help. Chemicals called polyacrylamides or PAMs are often used when fine silts and clays are present at the site of earth change. PAMs may be added to the sediment basin in order to help these particles to settle out in the basin. There needs to be adequate space and appropriate topography in order for an effective sediment basin to be constructed on site. Sediment basins take up a lot of space on a site. Sediment basins need to be designed by a professional engineer to ensure the basin will adequately contain sediment-laden runoff from the entire drainage area. In-stream sediment basins, also known as sediment traps, are typically not recommended and may not be constructed without a permit. Here is some basic information about design of sediment basins. The drainage area for a sediment basin can be up to 100 acres. If your site is even larger, you may need multiple basins. A well-designed sediment basin should have a length that is 4 times the width, with the inlet and outlet located opposite each other on the shorter sides of the basin. This design should allow adequate space for larger particles to settle out before the water exits the basin. Basins are typically used in conjunction with other BMPs. For example, on sites with clay soils and fine silts, a PAM will need to be used in order to settle out these small soil particles. We cannot design a basin big enough to settle out these fine particles naturally. Baffles can be used to increase the flow length, which in turn increases the residence time in the basin. This may be especially important when site constraints do not allow for a more typical design shape. The basin depth should be a minimum of 2 feet deep, but in some cases should be deeper. The depth is calculated by taking the length of the basin divided by 200. The outlet from the pond may be a standpipe with a gravel collar or a spillway. The outlet must be stabilized and an emergency overflow should be installed in order to prevent erosion in the case of an extremely large storm event. Sediment basins should be constructed before any other land clearing or grading is done. If a sediment basin will be converted to a permanent stormwater basin at the end of the project, require the contractor to perform needed maintenance on the basin, including dredging. Don't rely solely on your sediment basin for sediment control. Have appropriate erosion control measures and other sedimentation control measures in place on site for volumes over 80,000 cubic feet. The width of the basin should be equal to the cubic root of the product of the volume times 12.5. For our example, this is 111 feet. As we previously discussed, the length of the basin should be 4 times the width, or 444 feet in this case. The depth of the basin should be equal to the length divided by 200. In this case, the depth equals 2.2 feet. Remember that the minimum depth for a sediment pond is 2 feet. So, for this example, our basin would be 111 feet by 444 feet by 2.2 feet. What if we change conditions on the site and we divert all offsite water? How does that change our basin size and dimensions? Again, the capacity of a sediment basin should be equal to the volume needed to contain 1 inch of runoff from the entire drainage area, which is approximately 3,600 cubic feet per acre. We have a 10-acre site with off-site water diverted. 10 acres times 3,600 cubic feet per acre is equal to 36,000 cubic feet. Our sediment basin needs to be able to hold about 1/3 of the amount of water as compared to example 1. For this example, we use the formula for calculating length, width, and depth for volumes less than 80,000 cubic feet. To determine width, we calculate the square root of the quotient of the volume divided by 8. For our example, this is 67 feet. We know that the length should be 4 times the width, or 268 feet. The calculation for depth is equal to the length divided by 200, or 1.3 feet. However, remember that there is a 2-foot minimum depth. So, for this example, our basin would need to be roughly 67 feet by 268 feet by 2 feet. Sediment basins need to be cleaned out when a sediment depth of 40 to 50% of the depth of the basin is reached. You may notice a pattern here. Several BMPs discussed in this training program need to be cleaned out when 40 to 50% full. Here is an example diagram of a basin with a close-up of the dewatering structure. Note that the dewatering outlet is towards the top of the water level. This should be the cleanest water since larger sediment particles will settle to the bottom of the basin. Notice that the inlet and outlet are on opposite ends of the long, narrow pond. The water needs to travel from one end of the basin to the other, which increases the retention time and allows more sediment to be removed. Here's the outlet structure. The perforated riser pipe is surrounded by wire mesh and a mound of gravel, which is used for filtering out sediment. A trash rack over the top of the riser prevents debris from entering the pipe and clogging the spillway. Geotextile fabric should not be used around the perforated riser because it can clog quickly. The formula for basin dimensions specifies that the length should be 4 times the width. But the developer may want a more aesthetically pleasing pond for the development. Or in some cases, site conditions don't allow for the ideal basin shape. We may need to use baffles to increase detention time. There are numerous configurations. The objective is to give the sediments time to settle out. Notice the suspended clays in the sediment basin. The stormwater runoff is still sediment laden as it exits the basin. A baffle could be added to the basin so that the stormwater runoff does not immediately flow out of the basin. There is a skimmer installed on the surface of this basin. Notice the white pipes. A skimmer is designed to remove the cleanest water from the surface of the basin, In this case, the water in the basin is still very sediment laden. In addition to adding baffles, PAMs are recommended if the soils on site contain clays or fine silts. The next BMP we will discuss is mulch, which is typically made from organic materials such as straw, wood chips, or compost. Mulch provides a number of benefits. First of all, mulch shades the soil and newly planted seeds, acts to hold in moisture, and protects against temperature extremes. Mulch can also keep seed, soil, and fertilizer in place and reduce erosion. Additionally, it suppresses weed growth. One disadvantage of unanchored mulch is that it may wash away during large runoff events or high winds and in areas with steep slopes. Much like grass, mulch will cushion each raindrop as it hits the surface of the ground. This helps minimize detachment of soil particles, which helps prevent erosion. Three options for mulch material are listed on this slide. Each type of mulch has its own benefits. Before placing mulch, the site should be final graded and seeded. After the mulch is in place, it may be anchored with a mulch anchoring disc, tackifier, or netting. For installation specifications for different types of mulch, the training manual may be referenced. In this photo, wood mulch is being applied in a landscaped area. Here, we see straw mulch being blown onto an area which has already been final graded and seeded. Hydroseeding is commonly used for residential and some commercial applications. This technique saves time because seed, fertilizer, and mulch are applied at the same time. Tackifier is sometimes added to the slurry as well. The advantages of hydroseeding are that it's cost effective. It provides mulch to hold in moisture while seeds are germinating, and it provides erosion control if a tackifier is added. The disadvantages are that erosion control is limited if a tackifier is not added. Irrigation is required during dry periods. The hydroseed needs to dry after application and before rainfall, and remote areas are inaccessible with a hydroseeder. Stabilizing a site with hydroseeding can be tricky because there are four factors to get right. Hydroseeding can be effective when we get seed mixture, mulch type, tackifier, and application rate right. Bonded fiber matrix is a newer product which is applied in the same manner as hydroseeding. It is a proprietary blend of seed, mulch, fertilizer, and tackifier. It has the same longevity and shear stress as netted blankets. It can be more expensive than netted blankets and does not provide as much moisture retention. The advantage of bonded fiber matrix is that less staff are required to complete the installation. It's important to be very specific on SESC plans when identifying the particular seed, mulch, tackifier, and application rates. If the SESC plan does not include specifics, the contractor may cut corners and use lower quality materials, or they may apply the materials at a lower application rate. After hydroseeding has occurred, regular inspections are needed. Pay particular attention to hydromulched slopes. Look for damage from wind, water, or human activities. Repairs should be done immediately. Dust control is a BMP which should be implemented when conditions are dry to reduce wind erosion across bare soils. Construction staging is the most effective and least costly solution to this problem. Keeping the amount of disturbed soil to a minimum at any given time helps to reduce the potential for erosion caused by both wind and precipitation. Leaving natural windbreaks in place is recommended if possible. Other techniques include the use of snow fence perpendicular to the prevailing wind, the application of PAMs, daily watering, and hydroseeding. On a large, flat, unvegetated site, sediment generated from wind erosion is generally greater than that generated by water erosion. The training manual may be referenced for more information on these dust control methods. In this photo, we see a water truck applying a dust control treatment in a large area of bare soils. During dry conditions, the need for dust control needs to be monitored daily. Polyacrylamides or PAMs are a recommended control measure on sites with clay or fine silt soils. PAMs can be sprayed onto bare soil as an erosion control measure. In addition, PAMs may be used in sediment basins to cause these fine soil particles to clump together. This clumping action is called flocculation. Without the use of PAMs, these fine particles would not settle out prior to discharge from the basin. If PAMs are used in an area which discharges to a water of the state, approval is needed through EGLE. Use anionic PAMs only because cationic PAMs will bind to the gills of fish and invertebrates and can result in fish kills. Many different polymers are available. It's important to use a laboratory test to match the right PAM with the soil type at the site of earth change. In some cases, vegetation alone is not sufficient to permanently stabilize a slope. Cellular confinement systems are a permanent control measure used to stabilize soil on steep slopes or in areas with high velocity of water. Soil is placed in each cell and then the area is seeded. Grade stabilization structures are used to carry runoff from one level to another. Energy dissipators are used to reduce the velocity of discharge. Here are some examples of practices used to dissipate energy, including a concrete weir, riprap, turf reinforcement mats, and concrete pavers. Terracing is a technique used to slow the flow of water down a slope and to promote infiltration. Scarification is a technique to provide some erosion protection prior to a runoff event. Horizontal grooves in the soil are created by driving a bulldozer or other tracked vehicle up the slope. This technique may also be used to prepare the soil for seeding. The grooves will help to hold the seed in place and retain moisture. Surface roughening is recommended prior to the placement of topsoil in order to improve the bond between the soil layers. Soil slippage is a possibility when topsoiling steep slopes. Three factors contribute to this problem. The first factor is high moisture content. Topsoil contains organic matter, which can hold and retain large amounts of water. By absorbing this water, the weight of the topsoil increases and it becomes more fluid. When possible, divert water away from steep slopes until vegetation is established. The second factor is slope steepness. The steeper the slope, the easier it is for heavy, wet topsoil to slip. The third factor is poor bonding, or a lack of a good bond between the topsoil and the underlying subsoil. To prevent slippage, the underlying soil must be roughened to a depth of at least 2 inches before applying the topsoil. After the topsoil is spread, it should be compacted. Planning the development to fit natural site conditions is a good way to avoid soil erosion problems. When working in Michigan, the unique weather patterns typical of each of the four seasons must be considered. Timing and staging are critical. The project schedule needs to incorporate measures for stabilizing the site prior to winter. If the project will extend into the next spring, a plan for temporary stabilization is needed. Working in the hottest part of the summer brings the need to consider the issues resulting from hot, dry conditions. If vegetation needs to be established in July or August, a plan to provide irrigation will be an important component of the SESC plan. Vegetation is of utmost importance because roots stabilize and bind soil to prevent erosion. Vegetation also slows runoff, filters out sediment, and shields soil from the impact of raindrops. Once the site is final graded, permanent control measures need to be installed within 5 days. The appropriate seed mix, fertilizer, and soil amendments need to be selected in advance based on site conditions. On some sites, sodding is used for more immediate establishment of turf. If beach grasses are being established, a technique called sprigging may be used. This report card highlights the pros and cons of native plants, turf grass, and annual cover crops. Native plants are great for habitat and long-term erosion control, but can take a few years to become fully established. From the report card, you can see that annual cover crops will establish quickly and provide excellent erosion control. Temporary seeding typically contains annual cover crops. If native plants are being used for permanent seeding, an annual cover crop is often added to the seed mix. Check the label on the fertilizer bag to determine the percentages of nitrogen, phosphorus, and potassium in the product. The first number is the percentage of nitrogen, the middle number is the percentage of phosphorus, and the last number is the percentage of potassium. In order to determine how much phosphorus is in the bag, you would multiply the percent phosphorus, which is 0.15, by the number of pounds of fertilizer in the bag, which is 50 pounds. In this case, there are 7.5 pounds of phosphorus per bag. Phosphorus fertilizer is typically recommended for new seed starts, but should not be applied to established turf grass unless a soil test shows that it is needed. Phosphorus attaches to soil particles and does not need to be reapplied on a regular basis. When excess phosphorus reaches lakes, algal blooms and excessive growth of aquatic plants can result. To determine the need for soil amendments, soil testing is recommended. Most plants grow best when the soil pH is near neutral, between 6.5 and 7.5. If the pH is too low for optimal plant growth, lime may be added. Lime is a soil amendment made from ground limestone rock and is commonly used to increase soil pH. Native grasses provide excellent long-term stabilization, but can take a while to become established. A seed mix using both native and annual grasses is typically used in order to provide rapid erosion control in the first year. On some sites, sodding is used in order to provide more immediate stabilization. Sod must be staked on steep slopes. It should be staggered or shingled to prevent water droplets from following an uninterrupted pathway straight down the slope, which can cause real erosion. Sod must be watered during the first season or establishment of the turf grass may fail. Sprigging may be done using a machine that cuts grooves into the soil, then mashes sprigs of grass into the grooves. Another method is to till up the ground and spread sprigs across the surface, followed by rolling the ground surface to mash the sprigs into the soil. Sprigging is not a method for keeping mulch in place, but can be an effective way of establishing vegetation. In Michigan, this method is often used when installing beach grasses. The training manual includes guidelines for planting non-native grasses and legumes, native grasses, and temporary cover crops. Recommended seeding dates and application rates should be followed for the best chance of successful establishment. If seeding during the summer months cannot be avoided, irrigation must be provided. Michigan Department of Transportation has developed approved seed mixes for a variety of applications and soil conditions. MDOT's specifications can be found online and may be referenced in the SESC plan. This concludes part 2 of this section on best management practices. Thank you for your interest and participation in this training.